Great. Well, yes, thank you very much. So indeed, as Roma said, I'm going to talk a little bit about Apollo granites and some in situ rubidium strontium isotopes that we've collected over the past year or so. All right. Um, Great. So lunar granites, I think it's worth just spending a couple of slides then just sort of going through what lunar granites are. And I guess we've heard a little bit actually about silicic volcanism on the moon already a bit today. But just to remind folks then that when we talk about granites on Earth, a granite is technically defined as something that consists of SiO2 and two feldspar, a potassium feldspar and a plagioclase. On the moon, on these sort of evolved melts, we also see another sort of phase. We see this potassium silica-rich glass as well. But you might have seen in the literature these things called felsites. Sometimes they're called granites. A couple of the fragments that we saw from Bree's calculon creep meteorite earlier known as granopheres, which reflects a particular textural type. So there's a bit of interchangeability, but effectively when I'm saying granites, I'm talking about very evolved silicic pockets of melt. But they're rare. They're found at a handful of Apollo landing sites and within lunar meteorites. And you can see there the mass fraction of granites within the Apollo collection means they're actually quite an understudied collection of lithologies. And they're rare because they're generally quite small. So they're generally found within breccias, class within breccias, typically no more than around a few hundred microns in size. And they're also found within soil fractions. This is an example on the right-hand side there of a granitic clast from Apollo 12 soil fraction, and it can range up to a few millimeters in size. But this rarity and this size of these granites means that actually it's been quite difficult to employ geochronometers to try and understand the timing of formation of these lithologies. And so really you've historically had to consume the whole clast in order to do bulk rock isotope geochemistry, or you've had to get lucky and find a zircon within a clast to be able to do some uranium lead dating or all those kind of methods. But the big picture really, and why we're interested in trying to understand the timing of these granitic formations, is that ultimately we've got our big sort of concept, big picture ideas of how the moon's evolved, things like lunar magma ocean, things like the onset of basaltic volcanism and mare volcanism. Um, by and large, these ideas have stood the test of time over the past sort of 50 years or so. But ultimately, to verify these big picture concepts, we have to account for all the different lithologies that we see on the moon. And granites are one of those areas where there's still a bit of debate and a bit of uncertainty in terms of how they fit into sort of the evolution and the development of the lunar crust. So understanding the timing obviously can help assess some of these different formation models. And so to drill in a little bit further, and we've heard about this concept earlier this afternoon, one of the popular hypotheses that gets talked about a lot in a lot of papers that have been published over the past decade on these lithologies is this concept of basaltic underplating. And this is something that happens on Earth, whereby you have a fertile crust. In this case, for the moon specifically, people argue for something that's creep rich. It needs to be creep rich to satisfy some of the trace element constraints that these granites display. But fundamentally, you have a sort of a very fertile crust that's incompatible element enriched, and you have some kind of heat source, probably some kind of magmatic intrusion that generates partial melting of this fertile crust. And this can potentially produce very large volumes of silicic melts, and has been argued, for instance, to be the reason why we have the silicic domes scattered around the lunar near side, things like Griffeisens that we've heard a bit about by Kerry this week. So one of the main issues, however, with this model is the issue of timing. And mostly, so this is just a plot on the right here showing different ages of different lithologies. You can see there's a range of uranium lead ages and a range of whole rock rubidium strontium ages that have already been published on granites. However, if you want to partially melt a creep basalt to generate these sort of very silicic and granitic lithologies, our age constraints of creep basalts are very poor at the moment, and the few ages that have been published suggest that actually they've got quite a young age. And so obviously we have to try and understand whether a similar mechanism could also be the case if indeed some of these older 4.3 ages are indeed crystallization ages. But I think it's worth bearing in mind, though, our understanding of creep-rich volcanism during this period is very poor, simply because there haven't been that many good ages reported so far. Basically, to sort of sum up here, I suppose, it's unclear then if these ages represent continuous magmatism, discrete melting events potentially formed by different mechanisms, or indeed, some of these ages could have been modified by impact shock modification. For the next few slides now, I'm going to talk a bit about our method of in situ rubidium strontium. This is really nice because it enables us to sort of preserve the petrographic context of these rocks while looking at some of the isotopic data. And I don't really have time really to go through the actual specific method. I'm very happy to chat more about this after the talk potentially, because it's a relatively new method as the new generation of quadrupole mass specs are filtering their way through different geochemical labs. We're seeing quite a few labs now setting this this method up over the past few years. So it's still in its infancy, but I think it has a lot of very powerful potential for advancing our understanding of small clasts in situ. So yes, I'm going to look at the good, the bad, and the ugly, really, of some of the isochrons that we've seen so far. So in reverse order, the ugly, if you will. Actually, these isochrons are quite pretty. They're not that ugly. Apologies, you probably can't see the colors too well. This is a fake colored element map using our SCM. But the main thing to take away from this particular class is that you've got a core consisting of SiO2 and plagioclase and potassium feldspar that looks fairly crystalline. And the whole class is mantled by this silica potassium-rich glass, probably reflecting some kind of shock melt. And so while the rubidium strontium chromometer is resistant to shock, it's not so resistant to shock wave effects like pressure effects. It is quite susceptible to modification by temperature. And in fact, actually quite low temperatures, you can start to diffuse rubidium and strontium on hundreds of microns over decades, even at temperatures as low as 700 degrees. And so by virtue of these clasts being incorporated into breccias and into soils, they undoubtedly probably have seen quite a bit of thermal annealing in their history. And I think we can see that in quite a few of the samples that we've investigated in our study. And so what we were interested in then with this particular class was, could we say something about the crystallization age based on the core? We were rather hoping to get something that was either a crystallization age or maybe something that was partially reset. And then potentially, if we were to look at some of the isotopic analyses, including this glass, we might get something that approaches more an impact reset age. However, what we get is the opposite of that, which is, I find, quite counterintuitive. So just to remind folk then who are not too familiar with the rubidium-strontium system, what we're talking about is rubidium-87 decaying into strontium-87. So this is radiogenic strontium. And on the left-hand side is a isochron that includes glass, and that gives an age of about 3.89. And on the right, we have an isochron that doesn't include glass, that just has potassium feldspar and plagioclase plotted, and we get a younger age. And so this is odd. So how do we explain this? I'm not quite sure what this means. It's quite unclear at the moment, but one thing that has been noted in the literature, that in some terrestrial rocks, people have noted and have done similar RBSR studies on whole rock fractions, that potentially during shock and the impact process, you can get radiogenic strontium-87, being incorporated into shock glass. So in the terrestrial setting, people were describing strontium being mobilized from biotite crystals into shock glass. Potentially, we're seeing a similar thing here, where the strontium is moving from the feldspars into the glass. This would explain why we have our age older when we plot isochrons that include glass, and could also explain why we have actually quite low initials for some of these isochrons. We also have some really rather strange clasts as well that also support this idea of glass potentially recording or capturing some radiogenic strontium. This is a very unusual class here that has a very large SiO2 crystal there, you can see. The light blue surrounding it is all this potassium-rich, silica-rich glass. And then rather strangely, all this green material, which you can probably see a bit more clearly on the side screens, reflects pyroxene crystallized throughout all these cracks and fractures, which is really quite unusual. But regardless, when we look at some of the isotopic analyses from this glass, we get a 4.44 GAH. This is improbable that this reflects a crystallization age. This is quite an old age. And so, again, along with quite a low strontium initial, perhaps supports this idea that this glass has incorporated somehow a lot of radiogenic strontium, giving this apparent old age. But I'll just wrap up then, I guess, with a few nice isochrons that do seem to be quite consistent with other reported data. This is a class, or there's a collection of clasts within this NWA sample that we dated, and we get a fairly nice isochron of about 4.14. This is consistent with some uranium-lead uranium-lead apatite ages, I think, from this sample. Cool. So that's good. I think that's quite encouraging. This nice concordant age between two systems probably does reflect a crystallization age for these clasts, so that's very encouraging. And then finally, the last sort of isochron I want to show you guys is this Apollo 14 soil fraction. There's a number of clasts from this Apollo 14 soil fraction, and we get a nice isochron of 3.99 GA. This is consistent with some whole rock data that was published on granites from this same subsplit in the 90s. However, as you'll see at the very bottom there, a zircon uranium lead age from this sample is much older at 4.3, and so there's a discordance here. And so I think really fundamentally this sort of shows perhaps the limitation of the rubidium-strontium system when looking at these sorts of granites, in the sense that at face value, it's difficult to say if you just have a rubidium-strontium isochron whether something necessarily reflects a crystallization age. You really do need to say something about the thermal history of these samples. And really, you do need, in some respects, to corroborate and look at many different isotope systems to try and understand the thermal history and the crystallization history of these samples, because clearly the crystallization age for this rock probably is closer to 4.3, and 4.9 is probably some kind of Imbrium impact reset age. So I'll just wrap up there with a few of these conclusions. So basically, as I just said then, really, we need to corroborate a lot of these ages if we want to understand the timescales of granite formation with lots of different isotope systems. But I think there's still a lot of value, however, in doing these kind of in situ analyses, because for the samples that are clearly disturbed, we can use that information to say something actually quite important about the shock and thermal history that these samples have experienced, and we can then use this information to help place constraints on other isotope systems that we may want to collect in the future or that have been reported in the literature to date. So yeah, I'll leave it at that and happily take any questions.
Question in the room. Yeah,
Anna.
If there's anyone else. Okay. So you're saying that the radiogenic strontium could be in silica, right? Is that what you were?
Glass.
In the glass. Okay. But I was wondering if you were seeing different textural features in these glasses. It could be that very often when we look at glasses in silica, we interpret them as just glass, but sometimes they could be a glass that is coming from a denser polymorph precursor, and that affects diffusivities of elements substantially. So maybe you have different kinds of silica and therefore different thermal histories of the silica glass.
So the glass is, so we've looked at the chemistry of the glass, and I don't think it's a polymorph of any other mineral, basically, because it has a bulk composition of an average granite. So it's definitely not some mineral that's undergone some kind of sort of extensive shock to form a glass or whatever. So it clearly seems to be an average sort of silicic granitic composition. So to me, it does seem more like it's probably sort of a melt, probably related to shock, I guess.